you get an A in it, and you take another 4-credit class, and you get a B in it, your GPA is 3.5, right? Right down the center. It's easy because they're equally weighted. That's an easy average. This isn't easy. So if you take diastolic plus systolic and divide it by 2, you're making kind of the claim that your arteries are exposed for an equal amount of time to diastolic pressure as they are systolic pressure. And that's not quite true. And so let me show you what this looks like. I'm going to redraw this pulse curve that you see on the top left. I'm going to draw it less accurately, but I'm going to do it to illustrate how this is calculated. Because what we're getting to is the concept of mean arterial pressure, which is something you're always going to see calculated for patients, because the importance of mean arterial pressure is it's not concerned with the heart. That's what diastolic, systolic, and pulse pressure are for. It's concerned with what pressure is your kidney exposed to. How do we know how much pressure you're shoving into your kidney every heartbeat? You can't just say diastolic, systolic, because by the time the blood reaches there, the pulse curve has changed slightly. And so you need a way to calculate an average between this number, diastolic pressure, and some kind of weird weighted average for that little pulse pressure that you have there. So let me show you kind of how this does it. So I do want you to be able to calculate this by the time we're done. You have the formula in your book, but I want to make this somewhat intuitive. Make it make a little bit of sense, hopefully. So we're going to use 120 over 80. I'll wait to write the 120. So this is arterial blood pressure on this side. So we have 120 millimeters of mercury. And over here, the bottom is just 1 second. That's it. So we're taking a snapshot in time, and we're going to, we'll say it's like someone with those 60 beats per minute. So we're just going to get one beat here that we're going to show, instead of the multiple beats that we saw in the other picture. So from 0 to 80, let's just think about what I've drawn so far. This line represents the pressure at 80 millimeters of mercury. Let me write millimeters of mercury just to be, so my chemistry professor will be happy with me. So 80 millimeters of mercury. So let's say that somebody actually is walking around in this situation. Like they don't have a heartbeat, like the person with the implant. What would their average pressure be in their aorta? It's an easy question. 80. 80, right? So that's it. That's all that's going on. So it's 80. So this crazy person with no heartbeat at all has an average of 80, and it's always the same. So that's an easy calculation. We're not like this, though. We have a pulse, and that pulse has kind of a triangular curve to it that on average looks like this. So again, it's a little less accurate than the picture before, because in reality there's a little curving going on, but that's essentially what goes on our way up to our systolic pressure, 120 millimeters of mercury. So now the question is, what the heck is our average blood pressure? And so there's a formula for this based in geometry, but essentially the question is, we've already established that for 100% of the time, 80 millimeters of mercury. So our average must be higher than 80, because we've added pressure to the system. The question is, for what proportion of this time were we at systolic pressure? And so before we figure that out, let's add our pulse pressure, just to remind you. From 120 to 80, that's our pulse pressure. So the pulse pressure is truly the only thing that's different between someone who doesn't have a pulse and us. And so what we have to do is figure out what proportion of time are your arteries exposed to this pulse pressure, which in this case would just be 40. And so roughly this triangle, this one in here, takes up about 1/3 of this total area. So this area and this area, 2/3, the triangle's 1/3. That look roughly right in terms of just the area that it takes up? I know I may not have drawn it perfectly. That was my intention, was for this pulse to take up 1/3 of the total area. Do you get what I'm saying? Because that's the answer. That's all of it. That's it. So the hard part, though, is putting it into an equation, sort of, but not really. All you have to do is take my sentence. Here's my sentence. The average pressure in your arteries is equal to the 80 that's always there no matter what, because that's your diastolic, it never goes below that, plus the pulse pressure, but the pulse pressure is only there for a third of the time, so you multiply it by 1/3. So the formula for mean arterial pressure, abbreviated MAP, is diastolic pressure, the 80, plus 1/3 pulse pressure. Just based on this. Now, one of the reasons it's hard to have any kind of intuition about this is they usually present this with not with a 0 point on the graph. They like start you right here. But hopefully you can appreciate that really all we're doing is taking the thing that's happening 100% of the time and we're giving it 100% weight in our equation. Then we're taking the thing above that, which is the pulse pressure, but since it only occurs for about a third of the time, then we only add 1/3 of it to get to our number. And so for this calculation, we've got 80 plus 1/3 of 40, which is 93.3. So this is our mean arterial pressure. That's the pressure that your kidneys are exposed to. That's the pressure that your stomach's exposed to, your liver, your retina. These are really important things. So people that have high blood pressure actually are worried mostly about this calculation, because this is sort of a perfusion pressure, not a how much work does the heart do pressure. And that's why it's really valuable. So for organs, every organ except for the heart, the mean arterial pressure is actually the more important one. And so if anybody's heard that the diastolic pressure is actually your important one, anybody heard that? No one? Yeah. This is where that comes from, because in this calculation, it's certainly more important than systolic. But it's more important for organs, not so much the organ of the heart. And so there's still a fear in individuals. There's still data to suggest that the systolic pressure is equally, if not more important for predicting heart issues. However, when you're talking about people with high blood pressure and every other organ in their body, it's going to be the mean arterial pressure that matters the most. So this is why you can't just look at one number. A lot of people walking around, especially young, healthy people, will actually have quite elevated systolic pressures. But as long as their diastolic pressure is a little below average, they're not worried about their organs that much. They could be worried about their heart. But the mean arterial pressure is a very important one to calculate in yourself as well. This should be equally as valued as your systolic and diastolic. Clinically it is, but a lot of times, you go to the grocery store, they don't give you the map. But you can do the math now. It's pretty straightforward.
Yes.
So that's pretty much how it comes, how this is calculated. And if you take a cardiology course, you'll look at how this curve shape changes. So if this gets narrower, it actually makes this not 1/3, it makes it more like 1/5. And so your mean arterial pressure, even though your systolic and diastolic remain the same, at high activity levels, you actually change this formula a little bit. And so having this as a baseline, though, I think if you ever encounter it in the future, will help make it a little bit more intuitive to you. But at very least, I need you to know the MAP stands for mean arterial pressure, and I need you to know the formula. All right. Let's talk a little bit about arteries and veins. This is the picture from your textbook. So right at the beginning of the exercise 33A, I think, or 33 in some of your lab manuals. You got a picture of an artery and a vein in a microscopic level. I'm not